All right, this is the last segment of going over the practice final, and also I think the last time I'll post a video on YouTube for this semester. So this is the very end until the final at least. We're going over the last 6 problems of the exam. There's 24 problems in this exam. It's a long exam, but I guess that's good in most ways. And we've done 3 of the 4 before this. This is the last 6. It's number 13 as listed here, but that's really number 19 starting from the beginning, because the first 6 sort of don't count in this numbering. All right, so number 13 here, as listed anyway, says an enzyme obeys Michaelis-Menten kinetics with inhibition. At 310 K, the Kcat is 1,000 seconds per -1, and the Km is 1 micromolar. The Ki value is 1 micromolar, and the Ki prime value is 10 micromolar. Then it gives the energy of activation for the Kcat step as 60 kilojoules per mole. And it also gives the K1 value, so this is not Km, but the actual K1 value of 10 to the 10th, molar to the -1, seconds to the -1, and a K-1 value of 9,000 seconds to the -1. And then it gives the energy of activation for both of those and says that it's 0. In other words, there's no barrier at all for these reactions. That's not realistic, but it makes the calculations easier, as we'll see down below. All right, then it says, in addition, that for the binding reaction of enzyme to inhibitor, the enthalpy is -20 kilojoules per mole, and for the binding reaction of enzyme substrate complex to inhibitor, it's also -20 kilojoules per mole. Then it says, here's the bottom line finally, find new values for all of these parameters at 320 K, so after raising the temperature by 10 degrees. So the first, we just have to go down the list then. Number 1 is find Kcat at 320, and that's just an Arrhenius problem. We know the EA, it's 60 kilojoules per mole. We know Kcat1, it is 1,000 seconds to the -1. And so plugging the numbers in and remembering that that 60 kilojoules becomes 60,000 gives 2,070 seconds to the -1. Notice that the barrier height here is 60. It's a bit bigger than 50. But the rule of thumb still more or less applies. It's more or less doubled when raising the temperature by 10 degrees. All right, then K1 and K-1 we're going to need in order to find Km, right? Km is equal to, here it is down here, it's equal to K-1 plus Kcat divided by K1, and so we're going to need those K1s and K-1s in order to get Km. But this part is easy because the energy of activation is 0. If the energy of activation is 0, then these are rate constants that don't change with temperature. Remember that as the energy of activation gets smaller, the sensitivity of rate constants to temperature also gets smaller, and if you get the energy of activation all the way to 0, then there is no sensitivity whatsoever. They don't change with T, and that's what's happening in this case. That's why I set the energy of activation to 0 up here, because it makes the calculation shorter and easier in what would otherwise be a very long calculation. All right, now we can calculate Km. The K1 and K-1 values are the same as they were. They don't change with temperature. The Kcat, we just calculated, the new one. And so plugging the numbers in, we get that Km2, the one at 320, is 1.11 times 10 to the -6, which is 1.11 micromolar. Originally, Km was, where is it? There it is, half and half, 1 micromolar. So the change in temperature didn't change it very much, and it's useful to see why in this case. It's because the Kcat equilibrium rate constant is the smallest of all these things, right? So it makes relatively little difference compared to the 9,000 for K-1 here, or the 10 to the 10 for K1. All right, Fourth, we want to calculate the new values of Ki and Ki prime at 320 K, and we're given the delta H's, 20 kilojoules per mole, minus 20 kilojoules per mole for both of them. And so this is just a Van 't Hoff problem. For Van 't Hoff, all you need is the delta H. And we have the delta H and the two temperatures, of course. And so Ki2, the new Ki, is Ki1 times the exponential of delta H over R times 1 over T2 minus 1 over T1. That's 1 micromolar for Ki1. E to the, there is one trick. The delta H's are given for the binding reactions, but Ki is a KD, it's a dissociation reaction. So we have to reverse the sign of both of them. So instead of minus 20,000, it's plus 20,000. And that's what's actually plugged in here. Everything else is arithmetic, and you get 1.27 micromolar for the new Ki value. It changed from 1.0 to 1.27. Notice that's a relatively small change, and the reason is that the delta H is small compared to 50,000, right? 50,000 works for Van 't Hoff too. If the delta H is 50,000, then we'd expect a doubling in 10 degrees. It's much less than 50,000, so we get much less than a doubling. It's the same calculation for Ki2 prime versus Ki1 prime. Yeah, virtually the same calculation, and in fact, the only thing that's different is that Ki1 prime is 10 micromolar instead of 1 micromolar, so you get 12.7 instead of 1.27. And that is it for that problem. All right, number 14 is one of these anthology problems where there's a whole bunch of short questions. The first one says, find the entropy change when 1 mole of ideal gas expands from 1 liter to 5 liters. This is just a standard plug-in problem. Delta S is NR log V2 over V1. V2 is 5, V1 is 1, and so it's log of 5 times 8.314 times 1, which is 13.4 joules per K plus, right? Since the gas expanded, it's of course intuitive that the entropy should increase. Problem number 2 says an isolated system can change from state 1 to state 2, and there's an entropy change associated with that of minus 5 times Kb. Notice that I've put the entropy in this case in units of Kb, and remember that Kb has units of joules per K, so it has entropy units, and so that's fine. This is a microscopic delta S, notice, because Kb, remember, is a very small number, 1.38 times 10 to the minus 23. So this is a microscopic entropy change for a microscopic system, presumably. The next question is, what is the relative probability, P1 over P2, what's the ratio of probabilities for observing state 2 versus observing state 1? Notice that this is for an isolated system. For an isolated system, probabilities are given by entropies, right, not by partition functions. Well, the entropies, sorry, they're given by W's, not the partition functions. The partition function is W in the case of an isolated system, so the probability ratio is the same thing as the ratio of the W values, which is the same thing as e to the delta S divided by Kb. Since delta S here is given in units of Kb, that's just e to the minus 5 or 0.0067, or a little bit more than about 7 parts per thousand. All right, the only thing tricky about that one is the microscopic units and the use of the isolated system here, which is something that we didn't do very much in the main part of the class. All right, part C, find the entropy change when a box of gravel with heat capacity of 1,000 joules per K changes from 300 K to 350 K. The only thing about this one is to realize that even when the system is a complicated thing, even if it were a house or something else that's got all kinds of internal structure, or a box of gravel in this case, which is obviously not uniform throughout, you can still have a heat capacity, and the heat capacity still controls everything, just like it does in more normal chemical systems. And so delta S is heat capacity times log of the temperature ratio. The heat capacity is 1,000. The two temperatures are 350 and 300, and that gives 154.2 joules per K. Again, the only thing tricky at all about this is the fact that we're applying the thermodynamic calculations and ideas to something that seems kind of non-thermodynamic at first, but it does apply. All right, next question. Find the difference in reaction-free energy. For a chemical reaction, A goes to B when the initial concentration is 1 molar and the B concentration is 1 molar, versus the very same reaction when the concentrations are 0.5 molar and 1.5 molar. So we're looking for a change in the delta G, which means we're looking for the delta G with these concentrations, the final concentrations, minus the delta G with the initial concentrations, 1 molar each. And if you, remembering that delta G is equal to delta G0 minus RT log Q, plus RT log Q, and then taking the difference, right, 2 here, delta G1 here, delta G0 plus RT log Q2. The delta G0s are the same, right, because it's the same reaction. So when you subtract these two, these guys are going to cancel each other, and you just get the second terms here, RT log Q minus RT log Q1. And using the properties of logs, that's RT log Q2 over Q1. Q1 is just 1, right? 1 molar over 1 molar. Q2 is 1.5 molar over 0.5 molar, which is 3. So it's RT log 3, which is 2.74 kilojoules per mole. Part E says, find the canonical partition function for a system with 3 states. Energy U1 is 0, energy U2 is 1 kilojoule per mole, energy U3 is 3 kilojoules per mole at 300 K, and then also find the probability that the system is in state 3, the highest of the 3. So first of all, Q is just the sum of the Boltzmann factors, right, for each of the 3 states. So it's e to the minus u1, e to the minus u2, e to the minus u3. Plugging the numbers in for the u's and the t gives you all these values, which you can compute, and you get about 2, 1.97. The probability is then e to the minus u for the state in question, state 3, divided by RT, divided by our value of Q. We already did this calculation, right? It's this one up here, which is the 0.3 there. So we put the 0.3 there, divided by 1.97, and you get about 0.15. Part F just says write the full rate equations for both A and B for a simple first-order reversible reaction. That's 2 elementary steps, right? A goes to B, and then B goes to A with rate constants K1 and K minus 1. So for A, just to go through things, I mean, this is a simple one that people, I think, would have no trouble with, but just to go through it carefully, A will disappear according to this first reaction, so minus K1 times concentration of A. It will appear due to the second reaction, so plus K minus 1 times concentration of B. And the rate of change of B is just going to be the negative for the rate of change of A, right? Because whenever you lose an A, you gain a B and vice versa. And so it's K1A minus K minus 1B. Part G, the last part, says if an elementary reaction has a forward rate constant of 100 seconds to the minus 1. Notice it's elementary, and the units are seconds to the minus 1, so it's got to be first order. And if it's got a reverse rate constant of 10 seconds to the minus 1, so also first order. What's the standard free energy change for reaction? Well, if you've got the forward and reverse rate constants, you can get the equilibrium constant. It's 10 in this case. And then you can use delta G0 equals minus RT log K, which gives minus 5.74 kilojoules per mole. All right, that was number 14, kind of long, but only because it had, what, 7 parts or something like that. Number 15 says, protein P binds ligand L with a binding reaction. P plus L goes to PL. At 300 K, the fraction bound to the protein is 0.7. The fraction of protein that has a ligand bound to it is what that means, is 0.7, and the free ligand concentration is 5 nanomolar. At 310 K, so we went up by 10 degrees, the fraction is 0.5, and the free ligand concentration is also 5 nanomolar. So basically, we just raised the temperature by 10 degrees, and the fraction bound to the protein changed. It went down, which means the KD went up, right? And so the question is, find the standard enthalpy and entropy of binding, delta H bind and delta S bind, assuming that neither of these guys change with temperature. So all this really is an Van 't Hoff problem, where instead of giving the equilibrium constants, we're given these fractions bound, but we can get the fractions bound, we can get the equilibrium constants from the fractions bound, and so that's what we want to do. So at 300 K, the KD is, just solving for KD here in this formula, this standard formula is L times 1 over the fraction minus 1, and that gives a KD, well, this is true at both temperatures, right, at 300 and 310. So at 300, using the 300 numbers, you get 2.14 times 10 to the minus 9, 2 nanomolar KD. And at 310, you get 5 times 10 to the minus 9, about 5 nanomolar KD. Notice that the KD goes up, as we expected, and it goes up by more than a factor of 2. So we expect a delta H somewhat bigger than 50 kilojoules per mole. All right, now we have the two KDs. We plug into the Van 't Hoff. Delta H is equal to minus R log of the two KDs, ratio of the two KDs, minus the difference between the two 1 over T's. And that gives 65.62 kilojoules per mole plus, right, because the dissociation, the KDs went up when the temperature went up, therefore the delta H had to be positive. Notice that this is the delta H of dissociation, however. The delta H of binding has the minus sign in front of it. And then using the standard way, the standard formula for getting the entropy, once you have the enthalpy and an equilibrium constant at 300 K in this case, could have used 310 as usual. You get, after plugging in the numbers, 52 joules per K per mole. Again, that's for dissociation, so binding is minus 52 joules per K per mole. All right, number 16. The Michaelis-Menten mechanism for enzyme catalysis is controlled by two parameters, Kcat and Km, and it gives a definition for Km. The two steps in the mechanism can be described by the two-hill reaction energy diagram below. In other words, here's one elementary reaction, actually one reversible elementary reaction, right? And here's another one, another reversible elementary reaction. This one corresponds to K1 and K minus 1, right? K1 K minus 1 backwards and K1 forwards. And this one corresponds to Kcat, and it would be K minus 2 backwards. That one we usually neglect, we pretty much always neglect, not because it's small, but because there's usually no product present. So the reverse reaction is just turned off because there isn't any product in order to go backwards to reactant. So first question, find the equilibrium constant for just the binding reaction. Notice the Kcat step has been left out in this. Just the binding reaction, K1 and K minus 1. Well, we have the two rate constants. They are 100. Where are they? K1 is 100 here, and K minus 1 is 1, both seconds to the minus 1. And, well, sorry, no. Backwards 1 is seconds to the minus 1. Forward 1 is a second order rate constant, right? Molar to the minus 1, seconds to the minus 1. Anyway, it's 100 over 1, which gives a K, an equilibrium constant for just the binding step of 100. Part B says find all the rate constants, K1, K minus 1, K2, and Kcat and Km at 300 Kelvin. So all these numbers were at 310. So we're going down by 10 degrees now. We have, where's the energy of activation coming from here? Let's see, this is an Arrhenius problem, but where did that 40,000 come from? I read through this problem, but you know what? It looks to me like something is missing from this problem. This guy also needs an energy of activation, and this guy needs an energy of activation. Oh, they're coming from the diagram. I take it back, sorry. The diagram shows us the energies of activation. And so, yes, after that, they're just Arrhenius problems. And so 40,000 is this number for K1, 60,000 for K minus 1, indeed, 50,000 for K2, and then K backwards is 60,000, but we don't use it. And using the normal Arrhenius formulas, you get 59.6, 0.460, and 26.2 for those three Ks. That's to be compared to 100, right? So it went down. Yeah, we're going down in temperature. That's right. That's right. 300 is the final temperature. 310 is the original temperature. So it went down by not quite a factor of 2 because the barrier height is a little less than 50,000. This one went down by a little over a factor of 2 because the barrier height is a little bit bigger than 50,000. And this one went down by, what was the original again? 50. Went down by about a factor of 2 because the barrier height is 50,000. So again, we can understand all three of those results. And that gives the Kcat of 26.2, and now we can fill in all the numbers for Km. It's K minus 1, K1, and K2. Putting in the numbers, we get about 0.447. What was the original Km? It was it given? Was the original Km given? I don't see it, so we don't have anything to compare to. We could have computed it up here with the numbers, but we didn't. All right, so those are the numbers. Part C says find the equilibrium constant for the enzyme substrate complex at 300 K. We now have the two rate constants at 300 K, 59.6 and 0.460, so that gives 129.6 for the rate for the equilibrium constant. That's to be compared to 100. So the equilibrium constant actually went up a little bit when we went down in temperature. That, of course, means that there's a negative delta G associated with that binding, as you can see from this equilibrium constant already. All right, that was number 16. Number 17 is a predict the melting temperature. It's a straightforward problem of predicting the melting temperature given the sequence of an oligo and the table of values at the end of the exam. And so let's just go through it because we haven't done a huge number of these. We have done a couple of them now. Here's our sequence, and I chose a repeating sequence like this. I often do in exams because it speeds things up, right? We've got two AT end groups, so that's this contribution. And then what else do we have? Well, we've got an AT contribution. We've got another let's go in order. We've got a TA contribution, and that's not the same. We've got another AT contribution, and so on. We can just count. There's only AT and TA contributions. Those are the only types. And it turns out if you count that there's 4 of the AT type and 3 of the TA types. Then, from the tables that we haven't bothered to look at, but they're there, the delta H for the initial base pair is 9.6, 17.2 for the delta S, 30.1 for each of the ATs, minus 85.4, and so on. Plugging all those numbers in, adding them all up basically, gives the delta H of minus 191.5 kilojoules per mole and a delta S of minus 574 joules per K per mole. And now we have to predict the melting temperature. Here's the formula up above we derived earlier. It's delta H of melting and delta S of melting, but these are delta H's and delta S's of annealing. Again, we have to be careful about that. So these minus signs go away. Those are going to become pluses, and indeed, there's plus signs here and here. And the concentration is 4 millimolar. This quantity is CT over 4, right? So it's 1 millimolar that goes in there. And that gives a temperature, a melting temperature, a predicted melting temperature of 303 K, or 30 degrees C. All right, last one. Number 18 is a question to find all of the parameters for the inhibited Michaelis-Menten mechanism from two plots, one for the uninhibited case and one for the inhibited case. And what is the inhibitor concentration? It says it right here, 0.2 micromolar. And so this is one of the standard problems. It also gives the E0 value of 1 nanomolar. And it notes that there's some mixed units in the numbers that were given here. Notice it's seconds per millimolar here and micromolar to the minus 1 over here. So the units aren't consistent between the two axes, and that's going to cause some units factors to come in, so be careful about that. All right, from the uninhibited line, the initial, and we're reading off these graphs now, the initial intercept is 0.1 seconds per millimolar, right, which is 100 seconds per molar. Slope 0, from the uninhibited slope again, you can read off the graph, right? It's a dead straight, perfectly straight line. So it's rise over run, delta y over delta x. Delta y is 1. Let's see, delta y is 0.1, yeah, seconds per millimolar, and delta x is 10 micromolar to the minus 1. Now here's where the units issues come in. I convert them both to molar, so this becomes 100 seconds per molar, and 10 to the 7 molars to the minus 1, and now that the units are straight and consistent, you get 10 to the minus 5 seconds to the minus 1 for the slope of the uninhibited case. For the other line, we go through the same kinds of things. I won't go through it here just to save some time, but you get 200 seconds seconds per molar, and 3 times 10 to the minus 5 seconds to the minus 1 for the inhibited intercept and slope. All right, now we use the standard methods. Now that we've got the intercepts and slopes, we use the standard methods to get Vmax and Km and all that. Vmax is just 1 over the uninhibited intercept. That's 0.01 molars per second. Vmax is the slope over the intercept. Kcat is Vmax divided by the enzyme concentration, remember? So that's 0.01 divided by 10 to the minus 9 molar, right, for the enzyme concentration that was up there. And that gives 1 times 10 to the 7 seconds to the minus 1. Again, a very fast enzyme. Km is equal to the slope divided by the intercept for the uninhibited case. That's 10 to the minus 5 seconds to the minus 1. That's this number, divided by 100 seconds per molar. That's that number, and that gives 1 times 10 to the minus 7 molar, or 0.1 micromolar. It's a little bit better, little bit more convenient units for the Km value. All right, now we've got the two primary values. Now the inhibition values. Ki is equal to I concentration divided by alpha minus 1. Alpha is equal to the ratio of the inhibited slope over the uninhibited slope minus 1. We have both of those slopes. Those slopes, slope 0 is 10 to the minus 5, slope 1 is 3 times 10 to the minus 5, so that's a ratio of 3, minus 1, which is 2, which gives 0.1 micromolar for the Ki value. And the same thing, same process, except that it's alpha prime that we have to plug in. That's the ratio of the two intercepts. And those two intercepts are 200 for intercept 1 and 100 for intercept 2. So it's 2 minus 1 in the denominator divided by, and 0.2 up above, so that's 0.2 micromolar for Ki. And that is the end of that problem and also the end of this practice exam. And if people have questions, I think Mohammed has a recitation section scheduled for Monday, even though that's not an official recitation day. So I think we're going to be meeting tomorrow, and you can ask questions then.